As you can see from the title of this lesson, we're going to be studying exponential functions. Just exactly what do we mean by an exponential function? Obviously, it will involve exponents of some kind. I would like for us to first compare two functions so that we can determine what makes an exponential function. You are already familiar with the function y equals x squared, aren't you? You have sometimes referred to this as a polynomial function, or perhaps you have also used the word power function. Let's look at the parts of this power function. In particular, what I would like for you to notice is that the variable x is the base and the constant 2 is the exponent. So we will be selecting different values for the base, but we will always be raising those to the second power. Now compare that to this function over here. Here we have the constant base of 2, and that 2 is being raised to the variable power x. So in this particular function, we will be choosing different values for the exponent, but our base value is always 2. So this particular one is called an exponential function. In particular, then, a power function or a polynomial function has a base that is a variable, and it has an exponent that is constant. However, on the exponential function, the base is a constant and the exponent is a variable. So we can recognize exponential functions by asking ourselves whether or not the base is a constant or a variable, and whether our variable is in the exponent or not. Let's look at the formal definition of an exponential function. Let A be an arbitrary positive constant other than 1. The exponential function with base A is defined as f of x equals a to the x, or if you prefer, y equals a to the x. The domain of f is the set of all real numbers. We're going to be talking about that domain a little bit more later, so I really don't want to dwell on that particularly at this point. What I want you to notice here is A is arbitrary. That means any positive constant other than 1. We do not use a negative base for an exponential function. The reason for that is because with negative numbers we cannot always do certain exponents if our base is negative. We don't want to use a base of 1 because in particular 1 raised to any power is still 1. So we're going to rule out the number 1, but other than that, any positive constant can be our base. And if you'll notice in this definition, we're saying y equals the constant a, and the variable x is our exponent. Recall when we use this notation, f of x, this right here is identifying our variable. So our variable is x, and that appears in the exponent. We're going to be looking at several different exponential functions. Since we have already defined that these exponential functions can use any positive constant as a base, you might already be thinking I could have a base of 2 or 3, or perhaps even fractions like 1/2 or 3/4, which is true. But there's also another number that can be the base of an exponential function. That is the number e. You may or may not have learned something already about the number e, so we're going to look at that definition now. The formal definition for the number e reads like this. E is equal the limit as n approaches infinity of the quantity 1 plus 1 over n raised to the n power. Now, this definition may not mean very much to you if you've not ever discussed what we mean by this limit idea. Let me explain just a little bit what we're saying here. By saying that n approaches infinity, you're saying that n is getting bigger and bigger and bigger in a positive direction. So we're taking very large numbers here, like perhaps 1 million or 10 million or 100 million. We're taking that big number and putting it here, and also up here is the exponent. Now, if you want to look in your textbook, you'll find that they do some calculations using various values of n here, and it turns out that as you do these calculations, you can see that the value of e sort of tends to settle in, and you'll notice here I have e is approximately equal 2.718. Now, there are many more decimal places in the number e, but we're not going to remember those at this point. A little bit later, when we do some calculator problems, I'll show you on the calculator that your calculator has a button that will give you the value of e. Now, e is a number sort of like pi. You're already familiar with using the number pi when you calculate area or circumference of circles. And you know that the only way to write pi down exactly is to use that pi symbol. But when we calculate with pi, we very often use an approximate value such as 3.14. So the same thing is happening here with this e number. It's not important at this point that you particularly remember this definition. You might see this again when you study calculus, and it might be a little bit more important at that point that you concentrate on what this definition says. What's most important for you at this point is to know the approximate value of e, and when you see that letter e written in an equation or a problem, you know what its value is. Now that we have learned a little bit about what exponential functions are and about the letter e, the next thing I want to do is to do some calculator problems. You may be familiar on your calculator that you have an exponential key. In other words, a key that will help you raise numbers to various powers. That key on your calculator will either be labeled x to the y power or perhaps y to the x power. Different makes of calculators are slightly different in that regard. That key will allow you to raise any number to any power. What we're going to do next is to look at some problems where we're going to practice using that power key on your calculator. Now, I'm going to be using a particular type of calculator, and I will discuss how I enter things in this calculator. You will want to get your calculator and try some of these same problems and be sure that you're getting the same answer that I'm getting here with my calculator. As you probably are already aware, different calculators have you enter information in different ways. Some calculators you enter certain keys before others, and so you will need to either use your owner's manual or simply practice until you discover the way that your calculator operates. Let's look at those problems now. We are to approximate each value using a calculator. Now, I'm going to place my calculator up here. I realize that everything is not going to show up real clearly on the screen, so I will try to describe to you what I have on this calculator. You'll notice on this first problem that we are raising 2, this is to the 3.7 power. That may be kind of small on your screen, so I don't know if you can read that real carefully. 2 to the 3.7 power. You've probably perhaps not done exponents that were not whole numbers before. So what we're going to use on my calculator, there's a key right here. I don't know if you can see that. That key has an x, and then it has a little exponent of y after it. So to illustrate how this key is used on my calculator, I'm going to enter this base number of 2, and then I'm going to hit this x to the y key, and down here it's telling me I'm doing that power, And now I'm going to enter this exponent of 3.7, and then I'm going to hit my equal sign to complete that calculation. Now, as you can see, I have 12.99603834 and so forth. So since we are approximating, we'll need to decide how many decimal places we're going to keep in these answers. I think what I'm going to do is, let's say we keep 3 decimal places, which remember is the thousandths position in terms of the decimal place. So looking at my calculator display here, 12.996. The 6 is in that thousandths position, or the third decimal place. So looking just to the right of 6, I see a 0. So I will change all of these to zeros and keep the 6. So I'm going to say that this 2 to the 3.7 power is approximately 12.996. Now, while we're here, I might want to discuss a little bit about being somewhat sure that we have a reasonable answer. Notice that this 3.7 exponent is between 3 and 4. You know that 2 cubed is 8, and you know that 2 to the 4th power is 16. So since this exponent is between those two values, our answer here should be between 8 and 16, which you can see that it is. Okay, now I'm going to clear this out and let's look at our second problem. We have the base of 3 and we're raising this to the square root of 2 power. Now this may be the first time you've ever used an irrational number as an exponent, but that's okay. Our calculator can help us do that. Now what I'm going to do on my calculator again is to enter this 3 for my base. I'm going to hit my x to the y key to get my exponential function in there, and I'm going to put in my square root of 2 as an exponent. On my calculator, I will hit the square root key and then the 2, and then I'm going to hit my equal again to complete this calculation. Now let's see here. I'm getting approximately, I'm going to go to the thousandths or third decimal place. Notice this time I'll need to add 1. So 4.729 is going to be my approximation. Now again, can I be sure that this is reasonable? Well, you know that the square root of 2 is between 1 and 2, isn't it? The approximate value, in fact, I'll just show you right quick, the square root of 2 is approximately 1.414, etc. So this exponent is between 1 and 2. 3 to the first power is 3, and of course 3 squared is 9, and so our answer is between the values of 3 and 9. Okay, let's go on down to our third example here. This is kind of unusual. I have 5 as a base, and if you can see that, that's a pi as an exponent, 5 to the pi power. Now, most calculators will have a button for pi. My little pi button is right down here, so you might want to look for that button on your calculator. So to do 5 to the pi, I'm going to put in 5 as my base, x to the y, and then I'm going to hit this pi key, and you can see pi has come up here, and now I'm going to hit equal to complete my calculation. And again, if I round off to thousandths, or the third decimal place, that's where that 2 is. This is a 5, so I'll add 1 to my 2. So I have 156.993 as my approximate value. Now, does that sound reasonable? Well, you know that pi, being 3.14, is just a little bit more than 3, isn't it? Do you know what 5 cubed is? 5 cubed is 125. So we do expect our answer to be bigger than 125, which it is. Okay, now let's come down here to number 4, and you'll notice here we have that number e that we discussed a while ago, and I want to do e to the third power. Now, because e is a special number, our calculator has a special key for powers of e. Now, I know that you're not going to be able to see that on my calculator, but I want you to notice right here there's a little key that has LN written on it, and we'll talk more in a later lesson about what LN means. Right above that LN in my calculator, I have kind of an orangey color print, is e to the x. And so to get to any key that has that kind of orangey color print, I have to use my shift key that has the orange print also. This will be a good place for you perhaps to look at your owner's manual on your calculator to see if your calculator is different from mine. this e to the x key is set up for me to do powers of e. So I don't have to enter my base of e. What I'm going to do is to get to this e to the x key, and recall for me to get there I need to hit my shift key and then hit where that says e to the x in orange. And now you may not can read this, but right up here I have e to the x. Now I'm going to hit my exponent of 3, and then I'll hit my equal to complete this calculation. Rounding to the nearest thousandth, I'm going to change that to a 6. So I will have approximately 20.086. Now, since you may not be familiar with E, you may have a hard time deciding if this is a reasonable answer or not. So let's do this. We know from our previous definition that E is approximately 2.718. Now, since I'm using an approximate value here, I may not get exactly the same answer, but let's see what happens if I put in a base of 2.718 and I use this power key and raise that to the third power. Well, you'll notice I've got 20.079. Well, I'm off a little bit over here, but do you see that the numbers are fairly close? So I can be assured that I do have a correct answer here for my calculator. Okay, now this last problem, I put this down to be really different. I have a base of pi and an exponent of e. Well, let's see how we're going to do that. Okay, well, let's see. I've got a pi key, so I'm going to go ahead and put pi in, and I'm going to use my x to the y power to tell it I'm going to do an exponent. Now I need to figure out how to get e there. Well, e is equal e to the first power, isn't it? So notice I've already said I'm raising to a power, and now what I want to do is get e in there. So what I'm going to do is hit my shift and my e to the x, and I'm going to put a 1 in for that exponent, and then I'm going to complete my calculation. Now let me write this approximate value down here. I have 22.459 as my approximate value. Well, let's see. Would that sound reasonable? Well, let's see. Let's go back and do this. We know pi is approximately 3.14. All right, tell you what, let's do. Let's just go ahead and use the pi key. Keep that as much as we can do. But we know e is approximately 2.718. So what I'm going to do is hit my x to the y, and instead of doing what I did a while ago, I'm just going to put in 2.718 and then hit my equal key. And you'll notice here that I am getting an answer fairly close to what I had here. Now, another quick way to see if we're reasonable is pi is a little bit more than 3, and e being 2.7 is getting real close to 3, isn't it? It's a little less than 3. 3 cubed is exactly 27. So knowing that that 3 cubed is 27, this is a little more than 3, this is a little less than 3, we can see that this number does seem to be in the ballpark as far as being a reasonable answer. So I hope what you're seeing here is that we can do really unusual exponents with our calculator by using that x to the y key. The other thing is that we have this e to the x key, that if we have a base of e, then we can use that key to put in various exponents. I really strongly recommend that you take your calculator. You may want to pause this tape with these answers here on the screen and just take your calculator and play with it a little while to see if you can enter these values and get the same approximate answers here that I'm getting, just so you'll know that you know how to use your particular calculator. Now that we have done these examples, I want us to look at sort of a word problem that involves an exponential type function. Let's look at this problem. The growth of a particular strain of bacteria is given by the formula p equals 1.5 plus 4 to the 0.2t. Notice where your variable is. It's up here in the exponent, where p is the population in thousands and t is time in hours. So this would be considered an exponential function because our variable is up here in the exponent and we have a constant base. What I want to do with this problem is to just do a few calculations. We want to find the population after 2 hours. Now this is giving us a time t, isn't it? So this is saying let t be 2. Well, let's take this problem then. I have p equals 1.5 plus 4, and up here in the exponent I have 0.2 times t. Now if you want to, you could say, well, let's see, 0.2 times t, and my t is a 2. I'm getting what, 0.4 there? So you might want to go ahead and say that is to the 0.4 power. Okay? Well, we're going to do this problem like this, and then I'm going to show you another thing that you can do using your calculator. Okay, now with my particular calculator, I can just kind of chain this in the way this is written. Again, you may need to practice with yours to see what to do. I'm just going to put in my 1.5 plus, I have a base of 4. I need to hit my x to the y to get my exponent. My exponent is 0.4, and I'm going to hit equal to complete this calculation. And what I have here, of course, is a number of decimal places. I'm going to go ahead and do like we did a while ago and round off to 3 decimal places. So 3.241. Okay? So that's one way that we can do this. Now I want to show you another way here. Instead of going ahead and multiplying my 0.2 times my t, I'm going to look at this. I have 1.5 plus 4, and up here I'm going to put my 0.2 times, and I'm just going to substitute 2 for t, where I don't go ahead and multiply that out. And I want to talk about how we can do that using our calculator. Okay, I'm going to go ahead and put in my 1.5. Let me scoot that over. You've got a little bit of glare on here. Plus, I need my base of 4. Now I'm going to get to an exponent, so I'm going to do that x to the y. Now the problem here is, instead of having a single number for my exponent, I need to do an operation. So since I need to do an operation, what I'm going to do is use my parenthesis key, and I need to do 0.2 times 2. Now I'm going to close my parenthesis, and notice that gave me my 0.4 that we had a while ago. And now I'm going to hit my equal key to again complete my calculation. And if you notice, we have exactly the same answer that we had a while ago. So you can also just kind of chain that in like I've shown you in this particular example. Okay, now we want to find the population after 7 hours. So we're going to let t equal 7, aren't we? Okay, so p equals 1.5 plus my base of 4, and up here in the exponent I have 0.2 times my t of 7. Okay, so I'm going to do this one kind of like we did that second example a while ago. 1.5 plus my base of 4, use my x to y. I now need to enter my exponent, but I need to do a calculation. So parentheses, 0.2 times 7, close your parentheses, and see that did that for me, 1.4. Now hit equal to complete the calculation. I'm going to round to thousandths, so 8.464. Approximately 8.464. Now, of course, we noticed in reading the problem that p is given in thousands. So if I have 3.241 thousandths, I have 3.241 times 1,000. That, of course, is going to move my decimal, 3 places? So that's saying approximately 3,241 bacteria would be in that population after 2 hours. And of course, doing this in thousands, if you multiply by 1,000, you have approximately 8,464. So those bacteria are really growing rather rapidly, aren't they? You'll find that with exponential functions, basically, that always happens. Exponential functions grow very rapidly. Okay. Now that we have looked at just kind of using our calculator to do different funny-looking exponents that you may not have done in the past, I want to go back now to a basic exponential function, and we're just going to talk about getting some ordered pairs so we can look at the values. F of x is equal 3 to the x. Now you're used to taking functions and just arbitrarily picking an x value, substituting that in, and getting the corresponding y value. So what I'm going to do here is to start writing down kind of some ordered pairs here. Let's start by choosing x to be 0. Now remember, what we're going to do is substitute a 0 for x here. So I'm saying I have 3 to the 0 power. Well, what do you know about 3 to the 0 power? That's 1, isn't it? Okay, so I have the ordered pair 0, 1. Okay, well let's choose x to be 1. Alright, then if x is 1, I'm looking at 3 to the first power for my y value, which is 3, isn't it? Okay, well let's go ahead and choose x to be 2. Well, let's see, then if x is 2, I'm looking at 3 to the second power, which of course is 9. And let's just do one more whole number value here, 3. So if my x is a 3, I have 3 cubed, which is 27, isn't it? And you can see, of course, as we continue to let x get bigger, these numbers are going to continue to grow. So we could continue using our whole number values here. Now, let's look at using some negative values for x. Suppose I want to let x be negative 1. Well, let's see. If x is negative 1, I have 3 to the negative 1 power. Do you recall what that means? That means what? 1 over 3 to the first power, doesn't it? Or 1/3. Well, what about an exponent of negative 2? If I choose x to be negative 2, 3 to the negative 2 means 1 over 3 to the positive 2 power. If I simplify that, I have 1/9. So negative 2 would be paired with 1/9. Let's do one more of these negative exponents. How about negative 3? So if I have 3 to the negative 3, that means 1 over 3 cubed, or 1/27, doesn't it? Okay. So that would be a sample of some ordered pairs that we could get with 3 to the x. Now, I have not chosen any fractional values. Let's see, if I want x to be, say, the fraction 1/2. Well, let me write this down here. I'm doing 3, and I'm putting a 1/2 in place of x. Do you remember what we mean by 3 to the 1/2 power? Hopefully you remember that a 1/2 power is simply another way of writing the square root of 3. Now, we know that the square root of 3 is irrational. The exact value of the y there is the square root of 3. Now, we could, of course, take our calculator and do the square root of 3, and we would have an approximate value of 1.73 here. Notice also, I could take 3, use my x to the y, and I have a choice here. Since I know 1/2 is 0.5, I might just enter 0.5 as my exponent and hit my equal, and notice again I have that 1.73. Or I could hit my 3, my x to the y, and then I could do this calculation using a parenthesis, 1 divided by 2, close the parenthesis, hit my equal. Again, I'm at 1.73. So there are other ways that we can do this. In fact, there are some calculators that will have a fractional root or a fractional power key, just like we have an x to the y. In fact, my calculator does right up here. But I'm not going to go into that right this minute. I would suggest that maybe if you're interested in that, you talk with your instructor. If I choose a fraction like 1/3, then 3 to the 1/3 would mean what? The cube root of 3. And again, then, that's the exact value, and I could use a calculator to approximate that. We've already learned, of course, that we can choose such things like pi. We can do 3 to the pi. I think we did that a while ago. And we would get an approximate value here, wouldn't we? We could use some kind of an exponent like square root of 2. And we could take our calculator and do that 3 to the square root of 2 and get an approximate value that would go in here. I'm not going to do those at this point, but I just want you to get some idea about what happens when you have a function that looks like this. We can use all kinds of different values for x. Since these exponential functions are involving the use of exponents, the next thing I want to do in our lesson here is to just review some of the laws of exponents. We have already reviewed a couple of those when we were doing this exercise just a moment ago. But I have written down for you the laws of exponents that you should have had prior to doing this lesson. Let's just see if you remember what all these laws are. Okay, for the laws of exponents, notice this first one. a to the x times a to the y is equal a to the x plus y. Remember, when you multiply the same base, you write down your base and you add your exponents. Here we have a to the x to the y power. We call that a power to a power. Remember that when you have a power to a power, you multiply exponents. So you'll notice here we've written our base a, and we have xy, meaning x times y. Here we have a product inside a parenthesis with an exponent out here, ab raised to the x power. If you have a product inside your parenthesis, then each of these factors will get this exponent. So I have written a to the x, b to the x. Here we have a quotient, a to the x being divided by a to the y. Recall, when you're dividing and you have the same base, you write your base and you subtract your exponents, x subtract y. So I've written that here. On number 5, we have a quotient inside our parenthesis with an exponent outside. As you might recall, this would be like a fraction or whatever. Both the numerator and the denominator get this power when it's written like this. So a to the x divided by b to the x. Okay, we reviewed this a moment ago. If our base is not 0, right here, any other number besides 0 here, any number to the 0 power is equal 1. Again, if our base number is not 0, if we have a base number that's not 0 and we have a negative exponent, like negative x, remember a negative exponent causes you to invert that or write 1 over. And remember, when you invert it, write 1 over, your exponent becomes positive. And then this last one, I have a to the x divided by y, or x over y power, a fractional exponent. Recall that when you have a fractional exponent, the denominator of that fractional exponent tells you what root you are taking. So you'll notice here I have the y root of a, here I have the y root. My denominator tells me which root. The numerator tells you a power. And as it turns out, you have a choice of where you can place that power. You can say that you have the y root of a, the whole thing to the x power, or if you prefer, you can do the y root and do the a to the x power underneath here. You should have had these laws in the past and be familiar with them. So I just wanted to review those. If you have trouble with these laws of exponents, I would recommend that you go back and review these laws before you continue on with our lesson. Now, what I want to do is to emphasize to you that these laws do not change regardless of what the exponents look like. So you have probably already worked with both positive and negative and fractional exponents where you knew that you added exponents or multiplied exponents or whatever. Well, we're going to extend that idea by looking at some problems where we have some other more unusual looking exponents. Notice this first problem. We are to simplify. I have 5 to the square root of 3 power. Notice that quantity is raised to another power, which also happens to be the square root of 3. Don't concern yourself with how complicated this looks. This is simply a base number with an exponent and then another exponent, so we call this a power to a power. So our rule is when we have a power to a power, we multiply the exponents. So this is going to equal our base of 5. When I multiply the square root of 3 times the square root of 3, I get 3, don't I? So multiplying my exponents, I get a new exponent of 3. And then we know that 5 cubed is 125. Okay? Let's look at this one. I have 3 to the 2 subtract square root 2 power times 3 to the 5 plus square root 2 power. Again, don't worry about how complicated those exponents look. Notice we are multiplying and we have the same base, don't we? So our rule is that we write the base down and we do what with these exponents? We add them. Well, when we add numbers like this, we add this part together. 5 plus 2 gives me a 7, doesn't it? And then notice when I add the square roots of 2, I have a negative square root 2 and a plus square root 2, so those are going to add to 0 and cancel out. So I'm simply going to get 3 to the 7th power. Now I'm not going to take time to multiply 3 to the 7th power out, So if you're curious, you can do that. I'm just going to leave it at this point right here. All right, well, let's look at number 3. I have 7 to the 8 pi plus 3 power being divided by 7 to the 2 pi minus 5 power. Well, if you're dividing and you have the same base, remember what you do is you write your base number down. You take the exponent that's in the numerator. Now, since it has more than one term, I'm going to use a parenthesis. 8 pi plus 3 is what that exponent is. You take that numerator and you subtract the exponent down here. The exponent down here is 2 pi minus 5. And you'll notice, again, I used a parenthesis because that had more than one term. Now, let's simplify what we have up here. Let's rewrite that 7. Remember that this negative is going to do what with these signs? It's going to change them, isn't it? So I'm going to have 8 pi minus a 2 pi. That's 6 pi, isn't it? And then remember to change this sign also will be a plus 5. So 3 plus 5 is a plus 8. So I'm going to get 7 to the 6 pi plus 8. I hope that just with these few examples you get the idea that you don't have to worry about how complicated those exponents look. You simply follow those same rules that you've always followed. So you just need to remember, do I multiply exponents? Do I add exponents or subtract exponents or whatever? And then you just do that with whatever those exponents look like. Now, I also have some problems that I want us to work with that involve that new number e that we talked about. Notice again our instructions are to simplify. Well, let's see what we're doing here. We have e to the x plus 1 quantity to the second power. Well, we're squaring a binomial, aren't we? Okay, well, let's talk about this. When we square a binomial, the first step is to always square this first term, isn't it? Well, let's think about that. I have e to the x, and I want to square that. Look at this. This is a power to a power, isn't it? And our rule is we multiply those exponents. So when I square e to the x, I'm going to get e to the 2x power, okay? Now, on squaring a binomial, the next step is to multiply these two terms together and then times 2. Well, 1 times e to the x is simply e to the x, and then when we multiply by 2, we get a plus 2 e to the x power. And then remember, we square this term and we get a plus 1. Okay? Number 2, we have e to the 3x quantity to the 5th power. I have a power to a power. So what is my rule? Multiply exponents. So I'm going to write e. When I multiply these exponents, I get 15x, e to the 15x. All right. Number 3, e to the 5th times e to the negative 3 times e. Now think about what you're doing here. You're multiplying. Do you have the same base? Yes, you do. So our rule is when we're multiplying, we add up the exponents. Now this one doesn't have an exponent. So what does that mean? That means it's understood to be 1, doesn't it? Just like with anything else. So we're going to write the base of e, and we're going to add 5 and negative 3 give me a 2, plus 1 gives me 3. So that's equivalent to e cubed. All right, well, let's go on down here to number 4. This looks kind of like two binomials we're multiplying. But I want you to notice here, these are conjugates. E to the x, e to the minus x. The only difference is the sign in between them. So that's like x plus 2 times x minus 2 or something like that. Recall that when you multiply conjugates, you get difference of squares. Well, we've already talked about what we get when we square e to the x. We get e to the 2x, don't we? Okay, difference of squares. So I'm going to put a minus sign down. Now, let's take that e to the minus x and let's square it. What are we going to get there? Well, again, it's a power to a power. So we multiply those exponents and get e to the negative 2x. Okay, number 5. This is not any particular type of multiplication other than it's two binomials. So we're going to do this with our familiar FOIL pattern that we've already learned. So multiplying our first terms together, we'll multiply these coefficients and get 15. And then notice we are multiplying e to the x times e to the x. Let me write that up here for you. E to the x times e to the x. When you multiply, you write down the base and you do what with exponents? You add them. What is x plus x? Let me write it down for emphasis. Well, we know that x plus x is just 2x, isn't it? So I'm going to get e to the 2x here. Okay, my outside product, I'm just going to do it down here to save a little space. I have 3 e to the x times 4 is going to be a positive 12 e to the x. And my inside product, negative 2 times 5 e to the x, is a negative 10 e to the x. And since these are like terms, I can add them, and I'll have a positive 2 e to the x. And then finally, multiplying our last two terms, we get negative 8. I wanted you to see that working with that letter E doesn't really change any of the rules either of things that we've learned to do in the past. You just have to think real carefully about what it means when you square something and use those same laws of exponents that we've been reviewing to make sure that you have the exact quantity that you need there. Now, in this first part of the lesson, we've been concentrating a lot on how to do calculations with these exponential functions. What we want to do next is to turn our attention to doing some graphing of these exponential functions. So let's take a look at one of a kind of a simple exponential function to get us started. We want to graph f of x equals 2 to the x power. Now, a little while ago, we did a similar function with a little different base and talked about finding or picking certain x values and getting the corresponding y value. So what I want to look at here is, let's just kind of do a table over here. I'm just going to call it xy, even though this is written in the f of x notation. And let's start by choosing x to be 0. Now, if x is 0, 2 to the 0 power is 1, isn't it? Okay, since I have that point, I'm going to go ahead and locate it over here on my graph, 0, 1. Okay, x equals 1. Well, if x is a 1, 2 to the first power is 2, isn't it? So whenever x is 1, y is 2. So I have that point. Okay, let's let x be 2. If x is a 2, I'm looking at 2 squared here, which is 4. So when x is 2, I get 2, 4 right here. And this may not be on my graph because I may not have room, but let's just notice that if x is 3, 2 cubed would be 8. Well, let's see, 3, 2, 4, 6, 7. So it would be just a little bit taller than that right there. Now, we have learned that with our calculator, we can use other values. Like, for instance, if I use 0.5, which is halfway between my 0 and my 1, well, 0.5 is another way of saying what? 1/2? So let's think about that. If my exponent is 1/2, 2 to the 1/2 is the same thing as what? 2 to the 1/2 means square root 2. Well, we know square root 2 is approximately, so I'm going to get approximately 1.4. Well, let's go to our graph and notice if I go 0.5 for x, 1.4 is going to put me approximately right in here. I wanted to do that value to show you that if we pick fractional values in between these whole number values that we've picked, we're going to end up filling in and making this a smooth, continuous type curve here. So what I'm going to do right now is just to go ahead from this 0, 1 point and kind of start connecting these, and we can see that our function is rising up, kind of curving up like this. I'm going to put an arrow because you can see if we went over to x equals 4, 2 to the 4th power is 16, so it's going to get very big very quickly, isn't it? Now, I'm not finished with my graph because what I have not done is chosen negative values yet, so let's do a couple of those. If x is negative 1, remember 2 to the negative 1 means 1 over 2 to the first power, or 1/2. I'm going to write that down as a 0.5. So negative 1, I'm going to get a 0.5 or a 1/2 right there. If we let x be negative 2, 2 to the negative 2 is 1 over 2 squared, or 1/4. I'll write that right there, 1/4. So at negative 2, I'm only at 1/4. Now, can you see that as we continue to go this direction, like for instance, if we chose a negative 5 for x, I would have 2 to the negative 5 power, which is 1 over 2 to the 5th. That's 1 over 32. Now that's getting very, very small, but notice that it is still slightly above the x-axis, isn't it? In fact, if I chose something really way out there like negative 100, 2 to the negative 100 is 1 over 2 to the 100. This is still going to be positive. It's going to be very, very small. So what we see happening is that we will come this direction and we will approach the x-axis as an asymptote. Recall, that means that we're going to run along real close, but because we can see these values having a positive 2 as a base, we will never get a negative answer, nor will we ever get a 0 answer. Our graph is going to come very close to this x-axis, but it's not going to cross it. Okay? Now, while I have this graph here, I just as a comparison want to show you real quickly, what if I look at the graph of y equals 3 to the x? Let's just pick a few values here and see what happens with this 3 to the x. I'm going to see if I can use a red pen to graph that a little bit differently. I'm not sure how well that's going to show up, but let's see. Notice if I choose x to be 0, 3 to the 0 is still 1, isn't it? Okay, so I'm still going to have that 0, 1 power right there. Now I can tell this may not show up very red, but we'll get by anyway. If x is 1, 3 to the 1 power is 3, isn't it? Notice then when x is 1, 1, 2, 3, I'm right up there. If x is 2, 3 squared is 9. So notice at 2, I'm going to be all the way up to 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, way up here. I hope what you're seeing is that even though this 0, 1 point was in common, the 3 to the x graph is going up faster than the 2 to the x graph did. And the reason for that, of course, is that my base is bigger. Now, let's go in this negative direction for a second and see what happens. If x is negative 1, 3 to the negative 1 means 1 over 3, or 1/3. Well, a while ago, for this other function, negative 1 gave me a half. So here, 1/3 is going to be below that 1/2. So here's kind of what happens here. That's kind of difficult to see. My 3 to the x graph has the same point 0, 1 that my 2 to the x graph had, but it will rise faster going to the right, and it will come down faster to the left. So these two graphs actually cross each other at that point 0, 1. Now I think you can see if we chose an even bigger base, like say 4, we would go up faster, down faster. But again, if we use a base of 4, what is 4 to the 0 power? It's still 1, isn't it? So that would still go through this point right here. Now, I wanted to look at this function kind of separately here. That's our new number e, isn't it? And so what I'm going to do is to let us use our calculator a little bit to help us with this particular one. But we're going to do a table of values kind of like what we did before. If x is 0, I have e to the 0. Well, that's a positive number to the 0 power. So that is still going to be a 1, isn't it? I'm still going to have that 0, 1 point. You may be beginning to see that that point's kind of common to all of these exponential functions, isn't it? If I choose x to be 1, I have e to the first power. We know that is approximately 2.718. I'm just going to write 2.7. So whenever x is 1, I have 2.7, might be approximately right there. Now, whenever x is 2, I'm looking for e squared. So I'm going to go back to my calculator, and remember I'm going to use that e to the x key and put in an exponent of 2. So e squared is going to be about 7.4. I'm just going to round off to tenths since we're locating that 7.4. So 2, 1, 2, 3, 4, 5, 6, 7.4 would be just a little bit above there. So again, you'll notice that we're increasing, coming along like this. What if x is negative 1? Well, e to the negative 1 means, of course, 1 over e, doesn't it? 1 over about 2.7. But let's show you with our calculator that I can do that as well. What I'm going to do is to get that e to the x function down here. My exponent is negative 1. Now I can do that on my calculator by putting in my 1 and using my plus minus key to change it to a negative 1, and now I'm going to hit equal to complete that. So you'll see we're getting about 0.4. So I'm going to write down about 0.4, which is going to be a little bit below 1/2. Now if you continue picking values, you're going to find that again, as you pick these negatives more out this direction, you're going to have an asymptote here. Now let me slide this other one we did a moment ago up here, and let's take a look. Well, do you notice that these graphs are all sort of doing the same thing, aren't they? They're rising on the right hand side, they're coming down on the left and approaching this x-axis as an asymptote, aren't they? We learned over here that the bigger the base, the faster it goes up. Well, notice on e to the x, since e is about 2.7, 2.7 would be between 2 and 3, wouldn't it? If I had graphed this e to the x on the same graph with these, it would be between these two graphs because it would rise faster than 2 to the x, but not quite as fast as 3 to the x. And coming down here, it would be in between because, again, it would come down a little bit faster than 2 to the x, but not quite as fast as 3 to the x. Okay, now we've done sort of 3 different graphs here and learned that they kind of all have certain things in common. This 0, 1 point for one, rising here, and asymptote over here to the left. So what I want us to do is to look at a summary of what we've learned about these exponential functions. If we have f of x equals a to the x, where a is greater than 1. Now remember, for an exponential function, a can be any arbitrary constant other than 1. So here we're specifying that we're going to pick constants that are larger than 1. We will deal with those positive constants that are less than 1 a little bit later. Notice I've said the domain is negative infinity to positive infinity. Domain means the replacement for our independent variable, which in this case is our x. Remember, when we were doing these values, we picked positives, negatives, fractions. We could even do those things like pi, square root 2. So we can use any kind of a number up here in this exponent. So our domain is all reals. For the range, I have written 0 to infinity. And notice I use the parenthesis on that 0. It doesn't include 0, does it? We learned what? That on all of our graphs are approaching this x-axis as an asymptote, but our y values are always just above that. So they're always positive. They're never equal to 0. And that's what we're saying over here on this range. Between 0 and infinity, we're positive, we're above the x-axis. Notice x-intercepts, there are none. Our graphs for these basic exponential functions never crossed this x-axis, did they? Y-intercept, that point 0, 1, because no matter what this base is, if my exponent is 0, I'm going to get a 1. We have a horizontal asymptote of y equals 0, or in other words, the x-axis, as x approaches negative infinity. Now, I've said that's to the left. What we're saying here is x is getting very big in absolute value, but notice that negative is saying in the negative direction. So x is moving to the left, and as we go to the left, we approach this x-axis as an asymptote. Now, I've also said f of x is a one-to-one increasing function. It passes through 0, 1, which we've already talked about, and also 1a. Of course, if x is 1, a to the 1 is just a, isn't it? So that's an easy point to find. Let's review this idea. 1-to-1 means not only does each x have one y, but also each y has one x. I'm going to just put this graph back up here. Remember, to check for 1-to-1, you can use the horizontal line test. If you pass horizontal lines through this graph, it will cross the graph only one time, so it is 1-to-1. I also mentioned in this summary that my function was increasing. Remember, when looking at a function, you read it from left to right, just like a page of print. So as we move our eyes from left to right, our function is going up or it's increasing. You may want to kind of jot down these key points about exponential functions because they are very important in our understanding of exponential functions. Keep in mind, this is for the basic, simple little exponential function, a to the x. Now, I want us to look at graphing f of x equals 1/2 to the x. Now, you'll notice here, my base a is not larger than 1, is it? So let's take a look at that. Again, we'll just use a table of values and see what's happening. Well, let's start again with x equals 0. If you have 1/2 to the 0 power, do you still get 1? Well, of course you do. So we still have that same old 0, 1 point, don't we? If I let x be 1, 1/2 to the first power, of course, is 1/2, isn't it? Well, let's see. Whenever x is 1, y is 1/2. So I'll have that point. Okay, well, what if x is 2? Well, then I have 1/2 to the second power, which we know is 1/4. Okay, when x is 2, y is 1/4. Do you already see what's going to happen? If I move out to 3, if I cube 1/2, I get 1/8. So as I go to the right here, with larger positive values of x, my answers are going to get smaller. So from this 0, 1 point, I'm going to be coming down. And again, notice I'm going to get small answers, but I'm never going to get 0, nor will I ever get a negative. Okay, well, let's go to the left here with the next value of -1. What does it mean when you have 1/2 to the -1 power? Well, the negative on a fraction does what? It causes you to invert the fraction and change your exponent to positive. So we're going to get a 2. Okay, if x is -1, we get 2 right there. Okay, let's choose x to be -2. I have 1/2 to the -2. My negative exponent says invert the fraction and then change the exponent to positive. Well, that's just 2 squared or 4. So -2 gives me 4. Well, what happened with this graph? Well, it's just kind of backwards, so to speak, isn't it? I'm just going to put this one up here because it's just got the one graph on there. But notice, when our base was larger than 1, our graph was increasing. It was going up as we moved this direction. Our asymptote was to the left. Here, that's just backwards. Okay, our function is coming down as we move to the left. Our asymptote is the same x-axis, but notice it's to the right now instead of to the left. But notice we still have that 0, 1 point, don't we? So I think you're beginning to get an idea here of what happens when your base is a fraction, like 1/2. Now, I want to look at this function. F of x equals 2 to the -x power. Okay, now you should have learned that when x is replaced with a -x, that causes a reflection of your graph over what? The y-axis, doesn't it? Changing x to -x causes you to flip over that y-axis. So if we remember what the graph of y equals 2 to the x looked like, if I can find it, I'll put it back up here. It's this black one. Here's what y equals 2 to the x looks like. If we reflect that over the y-axis, our graph is going to come down like this, isn't it? Okay? Well, what I'm going to do is look at some values, and then we're going to see if that's what happens. So let's set up our table for x, y, and I'm going to start out, as always, with x equals 0. Well, minus 0 is still just 0, isn't it? So 2 to the 0 is still my 1, still 0, 1. If I let x be 1, be real careful here. X is 1, so I have 2 to the -1, minus x. That, of course, is 1 over 2, or 1/2, isn't it? So 1, I get 1/2. If I let x be 2, I've got 2 to the -2. 1 over 2 squared, or 1/4. Okay, so again, you're seeing this coming over here. If I choose x to be -1, let's be careful here. I have 2 to the -x, which is -1, and of course minus a negative is plus positive, so that's like 2 to the first power, or 2, -1, 2. And I think you can see that that's exactly what we expected to happen is happening. We have a negative x replacing x, so comparing this graph of 2 to the x with 2 to the negative x, if I take 2 to the x and reflect it over the y-axis, I get this graph. I also want you to notice, however, that this graph is exactly like the one we did just a moment ago, which was 1/2 to the x. Why would those two graphs be exactly alike? Well, let's see. Let's look at this function. F of x equals 2 to the negative x. Now, we know because of our rules of negative exponents that this means 1 over 2 to the positive x, doesn't it? Now, look at that. Is that the same thing as saying 1/2 to the x power? It will be, because 1 to any power is still 1. So I could rewrite 2 to the negative x as 1/2 to the x power. And so I should get the same graph that we had a moment ago. So having this negative on that x is kind of like having a fractional base, isn't it? Having looked at those two graphs, let's look at another property summary. Here we have f of x equals a to the x. Notice here a is between 0 and 1, so it's still positive, but it's a fraction. Notice our domain is still all real numbers. We can use any real number. Our range is still 0 to infinity. These graphs, even with these fractional bases, still stayed above that x-axis, didn't it? We still did not cross the x-axis, so there's no x-intercepts. We did cross the y-axis still at 0, 1, didn't we? Our horizontal asymptote was still y equals 0, or the x-axis, but notice now it's to the right, or as x approaches positive infinity, so the graph was reversed. We still have a 1-to-1 function, but notice now it is decreasing, okay? So if you look at the graph again, it's 1-to-1, but it's coming down as we move from left to right. But notice it still goes through that 0, 1 point, and again, whenever x is 1, I'm going to get whatever this a value is. Again, you may want to spend a little bit of time with this property summary and make sure that you understand what's happening here. Now, it's going to be very important that you get what I call a mental picture of what an exponential graph looks like. Just to explain exactly what I mean about having an exponential function, I want you to think about this. Let me go back down to the screen here. If I ask you, what does y equal x squared look like when you graph it, most of you are going to tell me a parabola, aren't you? So that's what I call a mental picture. If you have an exponential function a to the x, and this a is larger than 1, you should have a mental picture of a graph that looks like this. It goes through 0, 1, it has an asymptote to the left of the x-axis, and it rises this direction, okay? If you have y equals a to the x, and a is between 0 and 1, then you need to have the mental picture of your graph doing this. Your asymptote is now to the right, it still goes through 0, 1, and it's coming down from over here. So it's real important that you have kind of that mental picture and you know a couple of those specific points that we talked about. Because what we're going to do next is to look at graphs of more complicated type exponential functions where there may have been reflections or translations occur. And of course, anytime there's a translation, things move to different places. So intercepts might be different. Also, where the asymptote is located might be different. So let's go back to the screen and look at a different type of exponential function where we've had one of those things occur. Okay, let's look at this one. We have f of x is equal -2 to the x power. Now, first of all, I want you to be absolutely sure you understand this is not saying this. Let me write that down. What's the difference between this and this? Here, because of the parentheses, that would be saying our base is -2. Well, first of all, when we defined exponential functions, we said we couldn't have a negative base. So this is not what we mean. This means we're going to raise 2 to the x power, and after we do that exponent, then we're going to, if you will, multiply by -1 or find the opposite. Now, what I want to show you, first of all, let me rewrite this as a y value instead of using that f of x notation. Notice that if I multiply both sides of this equation by -1, I can rewrite this as -y equals 2 to the x power. Now look at this. If y is replaced with -y, think about y being replaced with -y, you are reflecting over the x-axis, aren't you? So this graph should look like 2 to the x that has been reflected over the x-axis. Now my mental picture of 2 to the x is going up like this. If I flip that over the axis, it should be coming down like this. Now I'm going to graph this as a reflection, and then we're going to look at some points to show that that's true. Remember that on 2 to the x, I go through the point, what, 0, 1? That would be right here. If I reflect that over the x-axis, that would be down here, wouldn't it? I also, on 2 to the x, if x is 1, I go through a y value of 2, in other words, 1, 2. If I reflect that point over the x-axis, I'm going down here. If x is a -1, I get 1/2. Okay, -1, 1/2. Reflect that over the x-axis, and I'm here. Now, I'm just going to go ahead and sketch in just with those 3 points right there what I think this graph is doing. Does that look like, let me kind of dot in, this is what 2 to the x would look like. We've reflected over x-axis. So you can see that we do have a correct idea here. Now let me just show you in terms of picking a few values here. If we do a table just to confirm what we have is correct. If x is 0, 2 to the 0 is 1 times -1 is -1. I'm going through 0, -1, aren't I? If x is 1, 2 to the first power is 2, multiplied by -1 is a -2. Am I going through 1, -2? Yes. If x is -1, 2 to the -1 is 1/2, times a -1 is a -1/2, and you can see my -1, -1/2. Hopefully what you'll learn to do is to not have to do this right here, but to learn to look at this as a familiar graph which has been reflected. All right, well, let's look at this one. I have f of x equals 3 to the x plus 2. Well, again, I'm going to do a little bit of rewriting here. I'm going to choose to rewrite that f of x as a y, 3 to the x plus 2. Now, what I'm going to do next, I'm going to take this constant 2 over here, and I'm going to subtract it and take it over here on the same side of the equation with my y value. So I'm going to write y minus 2 is equal to 3 to the x power. There's nothing wrong with doing that. That's perfectly good algebra. Now, what I'm going to do is kind of group this y minus 2 over here. What I want you to see is that this graph is kind of like y equals 3 to the x that has been translated to a new location. My new origin, well, let's see. Notice nothing was added or subtracted to x, so my x coordinate is still going to be 0. But look at this. Remember, if you have y minus 2, that's a translation which way? It's up 2. Now, one way that I tell my students to kind of remember that, if you take y minus 2 and set it equal to 0 and solve for y, you'll get y equals positive 2. So that's an easy way to find where that new origin is. So what I'm going to do is to go to 0, 2, right here, and I'm going to treat that like my new origin. So I'm going to put just a kind of a heavy dotted line going this way. That's going to be my new x-axis, so to speak. And of course I can leave the y-axis the same because it goes through that 0, 2 point. Now I'm going to ignore this and think about what does y equal 3 to the x look like, and I'm going to play like this is my origin. Well, if x is 0, y is 1, so I'm going to go up 1 from that new origin. If x is 1, y is 3, so I'm going to go over 1, 1, 2, 3. Of course I know that if I go 2, it's going to be 9 places up, so I don't have room for that, so I'll wait. If I use a negative 1 for x, 3 to the negative 1 is 1/3. So if I go negative 1, I have 1/3. Of course, I'm expecting this to look like 3 to the x, and I know what that looks like. So what my graph does is that same shape, but you'll notice it's just been moved up 2. Well, that's what this says, right? You're going to take 3 to the x and move it up 2. Well, what's happened is I have a new asymptote, don't I? My horizontal asymptote, I'm just going to write HA for horizontal asymptote, is no longer y equals 0 or the x-axis. It is now y equals 2. I will never cross that y equals 2 line because my graph has been shifted up. Notice that my new y-intercept is also in a different location. Instead of going through the old 0, 1, I go through the old 0, 1, 2, 3, don't I? Notice again, if I choose x to be 0 in my original equation, 3 to the 0 is 1, plus 2 gives me 3, doesn't it? So that is the correct point. And of course I have no x-intercepts because my graph is not going to cross that x-axis. So again, we're trying to get these graphs with as little work as possible, which means we're trying to recognize that this is simply like y equals 3 to the x, which we know what that looks like, but we've been shifted to a new location. Okay, well let's look at this one. I have f of x equals 3 to the x plus 1 power, subtract 1. Now again, I'm going to rewrite. I'm going to call this y, and while I'm rewriting, I'm going to take this 1 and add it, so I'll get a y plus 1 over here equals 3 to the x plus 1. Now I'm going to do a little grouping here. I'll group that y plus 1, and since all of this is in the exponent, I'm going to group that x plus 1. Now, this is going to be like the graph again of y equals 3 to the x, but this says something has been added or subtracted to both x and y. So again, it's a translation. Let's write down what that new origin would be. Well, let's take the x first. If I set this equal to 0 and solve for x, I get negative 1. In other words, x plus 1 gives me a shift to the left, negative 1. And y plus 1 gives me a shift down, because if I set this equal to 0 and solve for y, I get negative 1 also. So I have a new origin of negative 1, negative 1. Well, let's see. I'm going to go negative, whoops, better go negative. Negative 1 is right here. So I'm going to draw in a new x and y axis through this negative 1 point. Now I'm just going to put my little finger right here on that negative 1 because I'm going to play like that's the origin, and I'm going to graph y equals 3 to the x. Well, if x is 0, y is 1. Right there. If x is 1, y is 3, isn't it? So from my new origin, I'm going to go over 1 like x equals 1 and go up 1, 2, 3. Now I think since I have room, I'm going to keep going. If x is 2, 3 squared is 9. So from my new origin, if I go to the right 2, for x equals 2, I'm going to go up 9. 1, 2, 3, 4, 5, 6, 7, 8. Be right up there. And if x is negative 1, 3 to the negative 1 is 1/3. So from my new origin, if I go to the left 1, I'm going to be up 1/3 from there. Okay? So let's see where our graph is here. Notice the shape is the same. Still looks like y equals 3 to the x, doesn't it? But it's in a new location. Now, let's talk about, first of all, where is my horizontal asymptote? Well, what do I not cross now? I don't cross what? Y equals negative 1. What is my y-intercept? Well, let's see on my graph. Now, go back to the original origin here. It looks like 0, 2, doesn't it? Let's see if that's confirmed up here. If x is 0, I have 3 to the first power is 3. Minus 1 is 2. So that's exactly correct, isn't it? Notice this time I have an x-intercept. Looking at the original x and y axis, it looks like I'm crossing at negative 1, 0. Well, let's see if that makes sense. If x is negative 1, look up here. Negative 1 plus 1 is a 0. 3 to the 0 is 1. 1 subtract 1 is 0. So I do have an x-intercept this time. Remember, this is not violating those properties we learned, but it's simply because we have shifted our graph to the left and then down, and because we came down, all of a sudden we have an x-intercept. All right, well, let's look at this one. F of x equals e to the x minus 2. Well, I'm going to rewrite this as just y equals e to the x minus 2. And since all of that is in the exponent, I'm going to group that x minus 2. What should this graph look like? It should look like y equals e to the x, but I have a new origin where? Well, look at that x up there. What has been added or subtracted? X minus 2, if you set that equal to 0 and solve for x, you get x equals positive 2. So we have a shift to the right of 2. Notice there's nothing over here added or subtracted from y, so y is not shifting around, so y stays 0. Okay, well let's go to this new origin of 2, 0 right here. I'll need to sketch in a new y-axis for that new origin right here. Now we're going to play like this is the origin and graph e to the x. So if x is 0, e to the 0 is 1. So from my new origin, if that's 0, go up 1. If x is 1, e to the 1 is e, or about 2.7. So from my new origin, I'm going to go to the right 1 for x equals 1 and go up 1, 2.7 roughly. Okay. We know what the shape is. It's going to continue to go up like that, don't we? And then over here, of course, if x is negative 1, 1 over e, we did some values a while ago. I think it was like about 0.4, something like that. So we're going to come down. And notice because we did not shift up or down, my asymptote is still going to be this x-axis. All we did is shift to the right. Okay, so my horizontal asymptote is still y equals 0, or the x-axis. Now, I'm going to have no x-intercepts. I do have a y-intercept that we didn't stumble across just yet when we were doing this graph. Well, let's look at that if I want to get my y-intercept. And what I'm going to have us do is to go back to the original equation. To find y-intercepts, you let x be 0, don't you? If x is 0, you have e to the negative 2. E to the negative 2 power. Well, let me get my calculator. And let's do e to the negative 2 power. So I'm going to get to my e to the x, 2 negative for my exponent equals. That's about 0.135. I'm just going to say about 0.1. So I should be crossing just like about 1/10 above my x-axis right there. Now you'll notice in my y-intercept, I went ahead and wrote e to the negative 2. Why did I do that? Because this is the exact value of where I'm crossing the y-axis. The approximate value was about 0.1, and so we use that just to check our location. I have one other graph that I would like for us to look at. F of x equals e to the negative x plus 2. Well, let's see what's happening with this graph. I'm going to rewrite it. I'm going to call this y. I'm going to subtract this 2 and bring it over here with the y. So I have y minus 2 equals e to the negative x. And I'm going to group that y minus 2. Now we have a shift, don't we? This is going to be like the graph of y equals e to the negative x. I'm going to go ahead and write that on there. But my new origin is going to be where? Well, there's nothing added or subtracted from x, so that's a 0. But if I solve for y, I get y equals 2. So my new origin is going to be at 0, 2. So I'll need a new y-axis. I'm sorry, x-axis here. Now, my origin is here. So normally if I was graphing e to the x, I know I'd go through 0, 1, 1, 2.7, and I'd have a graph up here, right? But what is this negative in front of x doing? It's reflecting us over what? Changing x to negative x? Oh, I'm doing that the wrong way. X to negative x, we're reflecting over what? The y-axis. Okay, well let's think. My mental picture of e to the x looks like this. If I reflect it over the y-axis, it looks like this, doesn't it? Okay? So I'm going to graph something that looks like this from this new origin. So it's still going to go through that 0, 1. But this direction it's going to be up on e, or 2.7. And down this direction it's going to be on about that 0.1 that we got, or 0.4 rather, that we got before. Okay, well let's see if this could be right. Okay, it looks like our horizontal asymptote is y equals 2. It looks like my y-intercept is where? At 0, 1, 2, 3. Well, let's check that y-intercept first. If x is 0 up here in the original equation, minus 0 is still 0. E to the 0 is 1. 1 plus 2 is 3, isn't it? So we do have the correct value there. Now, just to double check another value, let's suppose we let x be 1. So I have e to the negative 1 plus 2. Well, let's go to that calculator again and see if we have an approximate value that is reasonable. Let me get my e to the x. I'm going to do a negative 1 exponent. Go ahead and complete that. And now I need to do what? Add 2. So that is approximately 2.4. Okay, well, let's go to our graph. Whenever x is 1, we're going 1, 2.4. So that's pretty close, isn't it? About 2.4. Let's check that x equals negative 1 value. Notice if x is negative 1 minus x is positive 1. So that would be e to the first power plus 2. Well, we know